Okay, so let's see what Fourier has to say about things. So the Fourier series claims that you can take any periodic waveform, we're going to use waveforms in time, and convert it into a weighted sum of cosine and sine waves at different frequencies. Of course, we might need an infinite number to get whatever waveform we started out with, but we can turn anything from a time domain into a series of sine waves. Now this is really useful for us because we look at frequency response plots of our circuits, and if we know what sine waves, what the frequency of the sine waves that make up our input, we can figure out what our output is. So the only problem we've got is that makes perfect sense for, say, even a triangle wave. You can sort of imagine sine waves making up triangle waves, but it seems somewhat suspicious when we look at a square wave. Square waves got these nice, really sharp edges, and sine waves have these curves, and the question is, even if we have a high frequency sine wave, could it really be possible that we can get a square wave out of a bunch of sine waves? If we look at a square wave as a function of time, that's equal to some constant times the sum, and in this case it's going to be an infinite sum because that's the only way we're going to get the really sharp edges on our square wave, of weighted sine waves, weighted by 1 over the number, and we don't need every one, we just need the odd ones. So we take our fundamental, number 1, then we take the third harmonic, 1/3 of it, then the fifth harmonic, 1/5 of it, add them all together, supposedly we get a sine wave. So our square wave is going to be our constant times sine of some frequency. Let's do 1 kilohertz because it's easy. Plus 1/3 sine of 3 kilohertz. Plus 1/5 sine of 5 kilohertz. And so on. Now, could that possibly work? Let's find out. Okay, so here's our experimental setup. We have an op amp configured as a summing amplifier. It has 5 inputs, 3 of them are shown. And it's just inverting with a unity gain, so it adds the first signal, inverts it, second signal, inverts it, third signal, all the way down to the fifth, adds them all together. So the output is the same as the input added together, inverted. But we don't care about sine waves, whether they're inverted or not. So what are we using as inputs? We're using 5 function generators. The first one we've set for 1 kilohertz and 10 volts peak to peak. That's our fundamental. The next one is 3 times that frequency, 3 kilohertz, but only 1/3 the amplitude, 3.33 volts. Next one is 5, not shown. The next one is 7 kilohertz, not shown. And then the final one is 9 kilohertz and 1/9 of 10 volts, 1.11 volt peak to peak. We're going to add those together and see what comes out. It's just a simple summing amplifier. Let's go see if this works. Okay, here's our experimental setup. We're going to use our scope to look at the output of the summing amplifier. And there's our 5 function generators. One thing that's not shown is there's actually a 6th function generator. You'll notice that when we add together the sine and cosine, they both are in the same phase. And the only way to get all of these function generators to start at exactly the same place is to start them with an external trigger. So in the back of each function generator, there's a trigger input. I've got that connected to yet another function generator that's starting them all at the same time, about 60 times per second. So let's take a look at what we've got. Here's our first function generator. It's at 1 kilohertz. And if we look at the scope, we can see it's 10 volts peak to peak. Second function generator is 3 times the frequency and 1/3 the voltage, so about 3.33 or so. Third function generator, 5 times the frequency of the fundamental. Two volts or so peak to peak. 5 kilohertz, 7 kilohertz, and then finally our fifth function generator is at 9 kilohertz. And about 1.1 volt, 1.2 volts. All right, let's take a look. So I start with everything off, turned on my fundamental. So that's my 1 kilohertz, 10 volt, peak to peak sine wave. Let's add in the first harmonic, the third harmonic, 3 kilohertz, at 1/3 the amplitude. Well, not quite a square wave, but you know, it's starting to look like it could be believable. It squares it up a bit. Now we'll add the fifth harmonic at 1/5 the amplitude, looking much better. We add the seventh harmonic at 1/7 the amplitude, and now it's looking more and more like a square wave. And finally we add in our last harmonic, the ninth harmonic that we have available at 1/9, and we get something that looks like it might be a square wave if we continue to add harmonics, only I ran out of function generators. So it looks like Fourier knew what he was talking about. That looks like we can indeed create a square wave out of sine waves as long as we have an infinite number of function generators at our disposal. And here we'll take them out one at a time. Take out the ninth harmonic, seventh harmonic, fifth harmonic, third harmonic. We're back to our sine wave. It's fundamental, first harmonic, third harmonic added together, 1/5 of the fifth harmonic added, 1/7 of the seventh harmonic, and 1/9 of the ninth harmonic.